Okay. Cleared out all that stuff out of the way. Probably start in a second. Hello, Rex. Alright, so where should I begin? I just wanted to thank Dr. Tinker again if he's watching, but just in general, for the first donation. That was very generous. I only had the link up for like, I think two streams, so that was pretty cool. Yeah, and I think the other thing I wanted to say was, yeah, I'd just been trying to do a couple things to improve the stream. I just ordered another board, so I'm all in for you guys. I'm already negative money. I'm already investing money in this. But yeah, I bought another board, so I might do like two boards next to each other. And then I'll have to figure out the angles or something. And yeah, probably gonna get a better camera eventually, so I don't have to keep using this laptop. And I have a monitor back there, which I'm pretty sure I could hook an HDMI cable to, and then might be able to have like the chat on a bigger screen. It's weird in OBS. In the MacBook you can like pinch it and make it bigger, but then you can't see the whole screen, so it's kind of annoying. I don't know why they do that, but maybe it's just a bug. Dual board. Oh, Stu has nice lo-fi music. Okay. So yeah, I'm just continuing with we're talking about vector spaces, and this is going to be lesson 15. So far we've defined vector spaces. We've talked about some properties of them. But now we're going to talk about maps between vector spaces, and this is a pretty common like category theory idea, which is like you want to not just look at the objects in a category, but all the maps between the objects, and somehow you recover information about all of the structure, from the maps. Or what is it? Yoneda embedding. You can like recover basically all the information, right? As long as it's small category, blah blah blah. Okay, so lesson 15. So I guess all that to say that it's important to study not just the objects in math, but the functions between them and the functions that preserve whatever structure you're studying. So in this case, it's linear structure. Yeah, so hopefully this is the last day with the small board. Oh, dual board, that's what you meant. Okay, I see. I totally missed that. So let's just start with the 3.1 definition. I think this is like the first definition in the section in 3A. And this is a pretty standard definition, so it just says a linear map. I mean standard in the sense that it's preserving the structure. So you'll see in a second. If we had a different algebraic structure, we would define maps in a similar way, but it would have to preserve whatever that structure is. So a linear map and if you remember all the way, if anyone watched the group theory videos from the beginning, a group homomorphism is a similar type of map, but in that case we just had a group operation. In this case we have two operations, which is the group operation on the vector space, but also the scalar multiplication. So both of those need to somehow be preserved with this function. So a linear map from V to W is a function from V to W. And then this function has extra properties. Mainly those two operations need to be preserved. Oh, also I was thinking, is it better to turn the... No, I'll just wait until I get the bigger board. I was thinking maybe I could move the camera a little bit and then put the board like more in the shot, but I don't know if it matters. So basically it's a function between vector spaces, and it needs to be additive. So it needs to preserve the group structure in the addition. So u plus v. So t of u plus v should be t of u plus t of v. And this should be true for all v, u and v. Okay, so in other words, the first property just says that the group structure under addition is preserved. So it's a group homomorphism under addition. Projection? Oh, projection. Linear maps, let's go. So what other maps do you know? Projection. Yeah, we'll get into the different types of linear maps, Rex, for sure. Projection. So yeah, addition is preserved under T, and then also scalar multiplication. So T of lambda V, or lambda U, is lambda T of U. All right, so, if you're having a hard time remembering this, one, it's only two things, so I don't know why it's that hard to remember, but, the pattern here is that it's a structure preserving map. So you have some function, this is just going to show up a lot in algebra. You have some function between your two structures, and then the structure on the domain needs to be somehow preserved through the function. So if you add in the domain, it should be the same thing as sending the individual values through the function first and then using the product on the codomain. Same thing with the scalar multiplication. Either I can scale on the domain, or I can send the individual item through the function and then apply some scalar on the output. And I should get the same thing. So the fact that it's structure preserving says that you have equality, that they're identical, they're equal. Okay, and then this should be true for all scalars, lambda, in your field. Okay, so basically it's a map between two vector spaces that preserves the addition map in the sense that it's a group homomorphism under addition, and then it preserves this scalar multiplication as well. So two properties. So what's why would you want a structure preserving map? Well, it preserves the structure in the sense that the image of the map is a vector space. You have a notion of a null space because we have a zero vector in W, so we can ask what's all the vectors that map to zero. That's also a subspace. So these things wouldn't be true if you just picked an arbitrary function t. It has to have these two properties, or else, yeah. Or else it's not structure preserving. You don't get any sort of algebraic information transferred from one to the other. Like if you don't have these two properties, basically. All right. Are there any questions about linear maps? See, I feel like I'm leaning over. That's why I wanted to let me try to move the camera a little. So I'm not like leaning. Is that the right way? Yeah. It's kind of tilted a little though. All right. I don't know if I'm gonna get it perfect, but yeah, we'll get a new board soon, so I'll have much more writing area. Okay, so no questions. Did you just get that, Rex? direction. That's a hard one to pronounce. Right, so yeah, so one thing that we want to have notation for is this set of all linear maps between two spaces. So usually we'll denote this like this. So it'll be a like script L, that's what Axler uses, V to W. So this is the set of all linear maps, V to W. And I guess maybe it wouldn't be so interesting and it wouldn't really require this special notation if it weren't the fact that this is also a vector space. So I think somebody in the Discord was asking me, can you look at all the subspaces of a vector space and use addition, and can you put some vector space structure on that? And I was kind of going through why it didn't really make sense with the normal way we would think of multiplication. But this is something that is a vector space. So you have two vector spaces. You can look at all the maps between them that preserve the linear structure. And you can put them all together in a set, and then this set also has a vector space structure. So let's go through what that vector space structure is. Right, so we have function preserving maps, and there should be some notion of adding two together. And if I take a scalar from the field, I should be able to multiply a map. So what does that mean in terms of the actual definition? Autobots transform glorp. Right, so yeah, so basically we just have to define these two things. So if I have two linear maps, T1 and T2, and if I have some scalar, lambda, in the underlying field, so what does it mean T1 plus T2? It's just basically the normal map you would imagine, I guess. So if you add two functions, actually, yeah, this is just the general notion of adding the value of two functions. They just happen to be linear in this sense, and when we add them, we get a new linear function. So T1 plus T2 of V is just T1 of V plus T2 of V. So just add them pointwise, basically. And then you can show that this new map is also linear. I don't know how obvious that is, but is that obvious that this is the new function is linear? I guess maybe you need to use some sort of probably check distributive property or something, yeah. Yeah, Rex was ahead of me. Yeah, so I guess to check fully that this actually, the sum is actually in this set, you would have to check that this new function is linear. Yeah, and then how do we define lambda T1? Some multiple of a function. Well, we just apply the function and then we take the multiple of it. So it's just lambda times T of V1, T1 of V1, T1 of V. Where T1 and T2 are just arbitrary linear maps. Okay, so we take two linear maps, we can add them together. We can scalar multiply a linear map by a scalar in F, and we get a new linear map. So that's basically all we need for a vector space. You just have to, if you were really careful, you would have to show that these two binary operations actually, satisfy all of the axioms, right? So you'd have to check all of those associativity properties, distributive properties. I can't even remember them all off the top of my head, honestly. there's all of like the associativity for the vector addition, associativity for the scalar multiplication. Then you have to check distribution on the field side, distribution on the vector side, and then there's probably like 2 other ones I'm forgetting. Okay, so given 2 vector spaces V and W, we can form this new set which contains all of the linear maps between the 2. Does anybody know what the dimension of this is? So if I know the dimension of V and it's finite, and I know the dimension of W and it's finite, what do we think the dimension of this new vector space is, this larger one? And Rex, if you know the answer, don't. Well, if you're the only one, then I guess you can answer. So we have, like, let's say this was V. Let's say V was like dimension 3, and W was dimension 5. So now we have a new vector space. I guess theoretically it could be infinite dimensional, right? But it's not. Give you guys a little bit to think if there is anybody thinking about it. I think it's a good problem to think about. I mean, we just learned about dimension, right? It's, how many linearly independent vectors do I need to span a vector space? We said for a finite dimensional vector space, that number was unique. So if V and W are finite dimensional, they have some finite list of spanning, linearly independent spanning list. Yeah, so I don't know. Anybody want to try to guess? Maybe there's nobody in the audience. Well, so maybe if anybody has taken like an earlier linear algebra class, you sort of go over how matrices encode linear maps in some sense, or if you're just talking about Fn or Rn or Cn or whatever, you can define multiplication by a matrix, and that gives you a linear map. So how big, if V is dimension n and W is dimension m, how big is the space of matrices between, maybe I'm making it too difficult here, but the point I'm trying to make here, though, is the linear maps, you can associate them with matrices, and they have they have some n by m size. So if this is dimension n, or do I have it backwards? I think I always do this backwards. N is so I think if this is n dimensional and this is m dimensional, then you can associate, we'll talk about later how you can associate a matrix to each linear map, and it'll be an n by m matrix. And so all of that to try to say that the dimension of this linear space, the maps between V and W, is n times m dimension. Yeah, it's the product of the, or sorry, no, wait, it's the product? Yeah, right, product, yeah. Product of the dimensions. Yeah, so we'll go into a little bit more why later this is the case. Well, like I said, I mean, one way to think of it is you can just think of every linear map is associated to a matrix, and matrices have n times m entries in them. So in terms of as a vector space over F, the matrices have dimension n times m, because I need I need one entry for each entry of the matrix, and there's n times m entries. So, I mean, that's not a proof, but you could imagine that n by m entries, because they need n times m numbers, you could imagine that the dimension is n times m. So what I'm saying here is that if the domain is dimension m and the codomain is dimension n, you can associate every linear map with a matrix, and matrices have dimension n times m, so you might believe that the dimensions multiply, like I was saying. Also, there's a notion of a tensor product between 2 vector spaces, and that has the same size. So if you tensor product 2 matrices of dimension n and m, you're going to also get n times m dimension. Yeah, so direct sums are adding, tensor products and maps between vector spaces, the dimension multiplies. Okay, so hopefully that gives you some sort of intuition for like why the multiplication is happening. It's because you get matrices. Matrices, the size of the matrix is always the product of the two dimensions. Okay, so we went over the vector operations in this bigger vector space. Right. Now also, if the domain and the codomain are the same, then it actually has extra structure. So it's a vector space because of these two definitions, same thing. But when V and W are the same, you can actually define a composition of maps as well, and that gives you a product. So instead of just being an F vector space, if your domain and codomain are the same, then you actually get an F algebra. And that becomes, a little bit more important. Maybe in physics you hear about operator algebras. I think those are usually like infinite dimensional, but yeah, I mean that's the same type of idea. Anytime you have a vector space and you have linear maps from a vector space to itself, and you look at all of those and you use the composition, that becomes a product. You get an algebra structure. So let me just write that down briefly because I think it is sort of important for like abstract algebra in general. So if the domain and the codomain are the same, if W equals V, then we'll usually write this. And then is an F algebra. With multiplication so if I take two linear maps, ST of V is just S composed with T of V. So I mean, the notation is even so similar, it's hard to even see that these are different, right? So this is defining the product S times T, and this is just saying that it's just S composed with T. So no circle, or I guess I could put like a star here or something, but usually we'll just write the linear maps next to each other, and it'll just be, the composition is just implied, we just defined it. So you get so in this case, it'll be n by n. If V is n dimensional, you'll have this new vector space, which is n by n, which is isomorphic to n by n matrices, and you can compose matrices or compose linear maps in this case, and that gives you an algebra structure because the composition preserves the linear structure as well. So because the composition is preserving the F algebra structure or the F vector space structure, that's what gives you this F algebra structure. Okay, so this, I already said it here, so this makes it an F algebra. So you have F vector space structure, F algebra is one additional property. Now you have a product structure where the product preserves the F vector space structure. Okay. So now let's just go through like a simple proof. So 3.10 says we want to show that the zero vector gets sent to the zero vector for any linear transformation. It's pretty much like the first thing you would prove for linear maps. Right, so this is 310. So suppose T is a linear map. Oops. So suppose T is a linear map. Show that T of 0 equals 0. And we did something pretty similar to this on Wednesday. I think it was like the first, I think actually Offendum, the person that just commented in chat. This is very similar to the problem that we did on Wednesday, your problem. So how would you show this? Actually, I actually came up with 2 proofs. I'm hoping they're both correct. I'm a little iffy on the first one. I feel like the second one is a little bit better. But yeah, how do we show that 0 goes to 0? So we basically want to show just using the 2 properties of linear maps, the fact that sums go to sums, scalar multiplication goes to scalar multiplication. How would we show this? Split the 0. Okay. Oh, I didn't. Yeah, okay, yeah, that's actually not how I did it, but I see. Yeah, that's yeah, that makes sense. Yeah, you can actually show it with both properties. Yeah, that's I proved it both ways. Yeah, I think I agree with Offendum. I mean, Rex, you're obviously correct as well, but yeah. So Rex, you're just saying you can look at like T of 0 plus 0, right? Is that what you're saying? For some reason, I wrote T of 0. I I wrote T of 0 is T of V minus V, and then I split it that way, which I think is actually technically still right, but unnecessary. Yeah, so split. So let's just do it that way. Yeah, we'll do it both ways actually. So we'll say this is proof 1. So T of 0 plus 0 is obviously just T of 0, right? Because 0 plus 0 is 0. And using the linearity property, or actually the group homomorphism property, the fact that it's a group homomorphism under addition. So this is T of 0 plus T of 0. And now we can use our left cancellation or right cancellation. It's abelian, doesn't matter. So T of 0 is equal to itself plus itself. So we can think of this as like T of 0 plus 0, like the 0 in W, is equal to T of 0 plus T of 0. And then because T of 0 plus 0 is equal to T of 0 plus T of 0, we use left cancellation. We cancel the T of 0s. We get 0 is equal to T of 0, or T of 0 is 0. Okay, so that's the first way. And then what would the second way be? Offendum, I think you basically wrote it out there, right? Yeah, f of 0 is f of 0 times 0, which is 0 times f of 0, and then 0 times anything is 0. So that looks good. So let's prove it the second way, just to be cool and say that we did. I think it's sort of the same idea though, right? No, I guess it is. Well, yeah, so actually really what we're proving in the first one is that, yeah, we're only proving that 0 goes to 0 under, yeah, all we really need is the group operations. We don't really need the vector space properties at all, because T is automatically a group homomorphism, and the group homomorphism already sends the additive identity to itself. We proved that in like 10 videos ago or something. So I guess we could have stopped before we even did the problem. We could just say, oh, it's a group homomorphism, send 0 to 0, we're done. But this is basically, I mean, this is the proof anyways, but so then the second way to prove it Second way to prove it, so proof number 2. So we take 0 in F, and we take the 0 vector in V, and we say that T of 0 times the 0 vector is T of 0. And by the homomorphism property, we can pull scalars out. So we can pull the 0 in the field out. So it's 0 times T of 0. And we know that we proved, I think actually we proved on Wednesday, that 0 in the field times any vector. So no matter what this was, even if we didn't assume it was 0, 0 times it would be 0 anyways. So, and then we're done. So T of the 0 vector is T of 0 times 0, which is 0 times T of 0, which is always 0. Okay. So, yeah, I don't know why. In my proof, I think it's still actually correct, but I wrote T of 0 is equal to T of V minus V, because V minus V is 0. And then that's T of V minus T of V. And then, yeah, I think you actually technically need to show a couple extra things, though, so this is probably cleaner. Because probably my proof depends on, I need to prove that thing we proved last time, like, -1 times the vector is the additive inverse, so I'd have to, like, include that in the proof as well. So this is definitely, like, less argument, I think. Okay, so Rex says, by the way, Sheldon emphasized that when we compose, we need to make sure the codomain of the first transformation needs to land as the domain of the second transformation. Yeah, that's definitely important. But yeah, of course, you never have that problem if you're talking about L of V, right? So if the maps are going from V to V, then the codomain and the domain always match up, right? You still think Leonard is better? So I don't know this Leonard book. I can't necessarily comment, but I gotta say, it's gonna be hard to beat the Axler book. I mean, Poison Mouse, maybe you like a little more like analytical book, more calculations, but we'll get to the calculations right after this chapter probably. It'll be much more about, FN, bases, and actually computing stuff, by hand, determinants and stuff like that we'll start doing. Oh, Leonard from Big Bang? What? Okay. Right, so T of 0 goes to 0. We just proved it 2 different ways. So now it's twice as true, of course, right? Yeah, that's actually the Leonard I was thinking of, Rex. We're on the same wavelength. I heard Leonard Susskind. That's the Leonard I was thinking of. To be 311. So this is the next section. I didn't pick any exercises from 2A. I guess I'll probably just go over a few on Wednesday. But also, I thought it was important to get to 2B today because I really wanted to define domain and range because, I feel like, yeah, it's just too important to not dive straight into. So there's going to be a definition for the null space. So null T or null space. Or what other names do they use in other books? I know I've seen some other things, I think. There's the null space. Oh, no. There's a range and image. Those are like synonyms. Yeah, I can't remember. I feel like there's other names for this though. I can't remember what the kernel, right? Yeah, that's the one. Yeah, kernel. Yeah, so I think actually kernel is probably more popular in like abstract algebra in general. Like you'll talk about the kernel of a group homomorphism. So I think kernel is actually probably more universal, but just in linear algebra they tend to use this like specialized language like null space. I mean null space because our vectors always have zeros, so you think of zero as like null, nothing. So, but of course, like these are abstract, so the zero isn't. I mean, it is a zero under addition, but it has nothing to do with the zero of integers necessarily, other than that it's also a zero. So yeah, so what is the null space? This is everything that maps to zero, basically. So for a linear transformation from V to W, null T is the set of all vectors V, yeah, such that T of V is 0. Okay. Yeah, so like I was saying, if T is a linear map, then you get these nice sets, and then they have the nice property that they're also subspaces. So if T wasn't a linear map, this was just a random function that was sending values to anything, then there's no reason that 0 would have to go to 0. There's no reason anything would have to map to 0, right? We could just send everything to some non-zero vector, right? And then this could be the empty set. If T wasn't a linear map, this could be the empty set. But we know that 0 goes to 0, and therefore we know it's not the empty set as long as T is linear. So yeah, so this fact is 313, which says that this is a subspace. So in Axler 313, he says the null space is a subspace. Is a subspace of V. It's very important that you remember that the null space, which one of these subspaces we're about to be talking about is a subspace of the domain, and which one is a subspace of the codomain. It's very clear from the definition that we're picking all the vectors in V that are mapping to 0. So this is a subspace of V. We'll talk about the range in a second, or maybe next time possibly, but the range is going to be a subspace of the codomain because it's going to include all the vectors that are in the image, all the vectors that are hit by some vector in the domain under the map T. So let's prove really quick that this is actually a subspace. The proof is like really simple, so should go very quickly. So we're going to prove this, but it's pretty straightforward. We're just going to use the properties of 0, the fact that like 0 plus 0 is 0, and the fact that this is T is a linear map. So assume x1 and x2 are in the null space of some linear transformation T. Then we want to show that x1 plus x2 is in the null space, right? Because how do we show that something's a subspace? We just have to show that if I take two vectors from the set and I add them together, they stay within the set. And then if I take a scalar multiple from the field and I multiply a vector in the whatever this set is, it should stay within the set. So basically, what I'm trying to do is I pick two vectors, we want to add them together, and we want to show that it's in the null space. So how do we do that? We show that it goes to 0 under T. So we just have to apply T here. And we have to show that this is 0. But because it's a linear transformation, it's additive, so this is t of x1 plus t of x2. And because they're in the null space, these are individually sent to 0 by the definition that we just erased. So this is 0 plus 0, which is 0. So t of x1 plus x2 is 0, therefore it's in the null space. x1 plus x2 is in the null space. And hopefully I can fit it here, but if we pick a scalar in the field, lambda, then lambda times x1 similarly is lambda times t of x1, which is lambda times 0, which is 0. So lambda times x1 also gets sent to 0, and therefore lambda times x1 is in the null space. So if I add two vectors in the null space, it's still in the null space. And if I multiply a vector by a scalar that's in the null, or sorry, if I multiply a vector that's in the null space by a scalar, then I also get 0. So it's closed under addition, it's closed under scalar multiplication, and therefore it's a subspace. And it's obviously a subset of V, so it's a subspace of V, because we're using the same operations of addition and scalar multiplication that exist in V. Okay, any questions before I go on? So I have one more page of notes I wanted to go over. Actually, yeah, just two exercises from 2B that I wanted to go over. I skipped the definition of range. I'm going to go over it next time a little more in detail, and we're going to go over the, has anybody ever heard of the fundamental theorem of, was it linear, yeah, is it fundamental theorem of linear algebra or fundamental theorem of linear maps? I believe maybe that's the name. Hopefully, if you guys have taken any sort of maybe like introductory linear algebra class, maybe you've seen this before, but I'm just trying to get a feel for who's heard of what. I think it's called the fundamental theorem of either linear maps or fundamental theorem of linear transformations, something like that. You've reached Lie groups. Well, yeah, we're not quite at Lie groups yet. Okay, so nobody's heard of it. All right, well then we'll go over it next time. But yeah, I'm not going to write down the definition of range yet, but it's a similar type of idea, except it's going to be defined as a subspace of the codomain. And then the fundamental theorem relates the dimensions of the two spaces. So you have the null space, the range, those both have dimensions, and then you have the dimension of the domain, and there's the fundamental theorem that relates the two dimensions. Dude, look above. Range is like in a function. Yeah, so I'm not going to write the definition for range. Actually, yeah, maybe I shouldn't even do these exercises without writing the, yeah, let's just write the definition really quick, just because I don't want to confuse anybody. Yeah, range. The range of a function is always a subset of the codomain. That's correct. Yeah. Whether it's a linear map or just a regular function, the range is always a subset. It's just the fact that if it preserves the linearity, then the range of the function becomes actually a linear subspace. but it's always a subset of the codomain, of course. Okay, so yeah, let's just write down range. So let's actually, I'll just give you the definition here. We'll talk about this again, but so this is going to be all vectors in the codomain where there exists a vector in the domain that maps to it. So it's all W in W such that there exists a V in V such that T of V is W. Of course, our map T is some linear map from V to W, right? Yeah, range equals image. Yeah, you'll see in some books they'll write like little IMT, or if you have a matrix, it'll be like IMA. Essentially, it's the same thing, or if it's not exactly the same thing, the idea is similar. Like for matrices, it's not literally the image of the matrix, but it's the image of the linear map given by multiplication by the matrix, so it's like essentially the same thing. But yeah, range is just the image of the map. I think you could probably even define range just for a regular function, right? It's just, you know, whatever things are hit in the image, right? So there's nothing here about linearity, right? We're just saying it's all the W's where something maps to W. So there's nothing really about linearity here. It's just the fact that if T is linear, then this range becomes a subspace of W. So that's the important factor here. And then so in 3b, the section we're talking about, if you look, I'm just going to go through the first two exercises because I think they're like, I didn't really go through the full section of 3b yet, so I'm going to pick kind of like easier ones, and hopefully we can still go through them and they have some value to you guys. So what we want to do is to give an example of a linear map T with the dimension of nullity equal to 3 and the dimension of the range equal to 2. Okay, so give an example of a linear map. So this is obviously hinting at this fundamental theorem. I haven't written it yet. We'll go over it next time. But I kind of wanted to give you a little bit of an introduction to it before I jumped right into it. So yeah, the fundamental theorem is fundamentally about these two dimensions. So it says that these two dimensions have to add up to the dimension of the domain of the map. If T is linear, V and W, or actually I think just V needs to be finite dimensional. If the domain is finite dimensional, then the dimension of the domain has to add up, has to be equal to the sum of these two. The dimension of the null space and the dimension of the range need to add up to the dimension of V, the domain. Not the codomain, so the domain on the first thing that's mapping, not the image. Right, so if we want to give an example of a linear map that basically we just want to send 3 of the basis vectors of V to 0, and we want to send 2 of the basis vectors, well, if it's an operator, we can just send them to themselves, right? An operator is a linear, is like L of V. It's the linear space of all maps from a vector space to itself. Those are all the operators. Right, so can someone come up with an easy example? I basically just kind of said it. So we need a 5-dimensional space because 3 plus 2 has to add up to the dimension of the domain, and 3 of the dimensions need to get sent to 0, and 2 of the dimensions need to not get sent to 0, basically. And they need to not be sent to linear combinations of each other either. So Right, right. Mouse. This is why I like studying the the abstract theory. I think this is why Axler likes going into this abstract stuff first, and then later we can talk about determinants, matrices, eigenvalues, and all that stuff. But yeah, I think it's important to understand this fundamental theorem that the domain has to have dimension 5 here. And to define a linear map, all I have to do is say where the basis vectors go. So essentially, this is just saying 3 of the basis vectors are going to go to 0, and 2 are going to go to some linearly independent plane. If it's Rn, it would be a plane, but of course it could be like Cn or something like that. More into the kernels. For x in R5, define f of x equal to x1, x2. I like that. Yeah. Fendum, that sounds pretty good. Start with 5, end with 2. Yeah, I mean, that's the idea, yeah. Actually, yeah, so we can, very simple solution, yeah, we can just fit it right here. Right, so t of x1, x2, x3, x4, x5 is x1, x2. Very good. Perfect. Yeah, so let's just go through this again real quick in the terminology that I was just using. So we can look at the standard basis here, and which one of the standard basis vectors goes to 0, and which one of the standard basis vectors goes to something that's not 0. Yeah, so x3, x4, so we can think of e3, e4, e5, the third, fourth, and fifth standard basis vectors, the ones that only have a 1 in that position. So the 0, 0, 1, 0, 0, that gets sent to 0. 0, 0, 0, 1, 0 gets sent to 0. And 0, 0, 0, 0, 1 also gets sent to 0. So E3, E4, and E5 standard basis vectors get sent to 0, and E1 and E2 actually just get sent to themselves, but in the codomain. And they are linearly independent. So the range has a two-dimensional space because these are the image of the 2 basis vectors here are linearly independent, and we sent 3 basis vectors to 0. So I guess I'm just kind of trying to reinterpret the problem. So not only do we get the answer correct, but you understand like why it's correct, and also, how you would have come up with this just out of the blue, right? You don't just pick this map and then, oh, it's the answer, right? You want to think, okay, I'm sending 3 basis vectors to 0, and I'm sending 2 to some linearly independent set. So I'm going to get a 2-dimensional space in the range. And in this case, it's basically just isomorphic to the xy plane that's sitting in R5 or F5, whatever the field is. Okay, so that one was pretty easy. Very, very simple. I guess maybe you have to prove it, but it's pretty simple to prove, right? I'm not gonna waste the time. Let's go to number 2. Any questions about this? I think this problem's pretty straightforward, but I think it really illustrates that fundamental theorem properly. The fact that these 2 dimensions have to add up. This has to be 5-dimensional. There's no other way to do the problem. So you're forced. The fundamental theorem forces the domain to have dimension 5. Okay, and then the last problem I wanted to go over today, so just number 2, again, we're just going a little bit slow with the exercises. We'll do more stuff next Tuesday, more like theoretical stuff, and then I'll do a lot of exercises on Wednesday. I think this is probably one of the most important chapters, and maybe 3B is probably one of the most important sections of that chapter. So 3B number 2. exercise 2. So this says, I just thought this problem was a little cute. So it says, suppose you have two linear transformations from V to itself. So this algebra. And they are such that the range of S is a subset of null T. So this is a subset. Hopefully that's clear. And now we want to prove oh wait, I didn't write the statement. So prove that ST squared is 0. Hey, famished integral. Right, so just the last problem for today. So we have two linear maps. The range of S, so everything S is mapping into V. The image of S is in, so everything in the image of S gets sent to 0 by T. That's what this is saying. That's okay. That's okay. So yeah, range of S being inside of null T, that just means everything that, all the, if we take any vector in V, we send it through the function S, and then we send that image through the function T, then it gets sent to 0. So that's what this is, just reinterpreting the definitions of range and null space. Okay, so why is ST squared? I kind of like, I think this problem's a little bit cute because, so what is ST squared here? ST squared is really, we have associativity under composition, right? So ST squared is really like ST composed with ST, which is really just ST, ST. And I can use the associativity property to associate the product in any way I want, right? So ST squared is the same thing as S times S times T. And what is T times S? Well, I know the image of S is inside of the null space of T, so all of the vectors in the image of S get sent to 0 by T. So this whole thing is just 0. This is the 0 function, because it sends every vector to something in the image of S, and then everything there gets sent to 0 by T. So if everything gets sent to 0, then it's just the 0 function. So it's S times the 0 function times T, and that's just 0. So ST times itself, you associate the middle product. That middle product has to be 0 because of the assumption. And you can also prove that if you compose any function with the 0 function, then that's also 0 because everything gets sent to 0 and then 0 goes to 0 under every other linear map. So yeah, I guess you kind of have to be careful here because we didn't really technically check that, S times 0 times T is 0, but yeah, you can show that pretty simply. Okay. I think that's basically it for today. I just did a couple problems, but I like to go over the problems that I feel they use the material, but like also kind of illustrate something else in an interesting way. So here, we didn't really do anything about range, so I wanted to illustrate something about the range. And this kind of just ties up null space and range in a nice way. I think there's some, this reminds me of another problem, maybe someone else out there remembers, but there's some problem about like if matrices are nilpotent, then like the product of them is also nilpotent or something. I don't know if anybody remembers a problem like that, but this one definitely reminds me of that. Did I get it right though? Is that the statement? Product of nilpotent matrices is nilpotent? I can't remember. But yeah, this kind of reminds me of that problem. Okay. I'm gonna stop the recording here for the YouTubes, but I'll be here if anybody wants to discuss more math for a little.